Hi, this is Abhilash, and today we are going to solve another problem from lead code, which is lead code 785 is graph bipartite. So the question is, there is an undirected graph with n nodes where each node is numbered between 0 to n minus 1. So I am given a 2D array, which is a representation of graph, where graph U is an array of nodes that U is adjacent to. That means I am being given an adjacency matrix. So more formally, for each V in the graph U, there is an undirected edge between the node U and the node V. And the graph has the following properties. So there are no self edges. So graph U does not contain an edge to U. There are no parallel edges. If V is in graph U, then U is in graph V. That is, it is undirected graph. And the graph may not be connected, meaning that there may be two nodes U and V such that there is no path between them. So these are the two cases and the different conditions for creating this graph. So a graph is bipartite if the nodes can be positioned into two different sets which are independent, A and B, such that every edge in the graph connects a node in set A with a node in set B. Okay, so this is a graph problem which can be solved by using something called as graph coloring. So graph coloring means that if I color a particular node, I will not, let's say I colored this node 0 with a color as red, then I cannot color the adjacent nodes with the same color. Okay, so I have to color it with either blue or a different color. The case where two different nodes which are adjacent have the same color, then that does not give rise to a bipartite graph. In that case, it is returned as false. And this is the case of a fully connected graph where there are no disjoint components. But if there were a case where there was another node which is completely disjoint from this particular graph, then we have to perform this graph coloring on both of these graphs. So in this case, we can see from this logic that if I color this node red, then that means I can color 3 with blue, but 2 is adjacent to both 0 and 3. So I have to make another different color for particular 2. So 2 needs to be colored with something other than red or blue. But that is the condition for which bipartite graphs fails. If the graph coloring value exceeds 2, that means that the graph does not have a bipartite feature. So in that case, 2 will be colored with something else. So let's say yellow. Now, if we consider 1, which is uncolored as of now, so you have 0 with the color as red, 3 with blue, and 2 with yellow. Now 0 is red and 2 is yellow. Both of them are connected to 1. So 1 cannot have this red color. 2 cannot have this yellow color, which it has. So 1 cannot have either red or yellow. So it can have the blue color because 3 and 1 are not adjacent. So they are at a distance of 2 to be precise, minimum distance of 2 via this path or via this path. So in this case, the graph coloring gives a value of at least 3 because we need at least 3 different colors to color this particular graph. So that is why it is returning as false. If we were looking at this particular problem, then in this case, we can partition this particular graph using graph coloring into 2 different sets, that is 0, 2 and 1, 3. Because 2 is not directly connected to 0. So this particular, if I color this with red, then 2 can also be colored with red because they are not directly connected. So if I color 3 with blue, then 1 can be colored with blue, right? Because its adjacents are both red in color. So in this case, it returns a true color. So here the graph coloring value is also 2, which satisfies the bipartite theorem. So in this case, we are going to approach this problem by using graph coloring. And for bipartite graphs, we will have 2 colors. Okay. So for this, we need to have some conditions So we are going to perform a BFS on the graph. DFS can also be done in this case, but due to simplicity, let us try to go with BFS approach. We need an initialization class that is a color vector, which stores the colors initially, right? So initially, all of them are, let's say, having a color which is, let's say, black or white. Okay, so that means all of them are unvisited. And as we move along a certain path in the BFS search, we'll be coloring the nodes as and when we get it. Okay, so keeping this in mind, we are going to initialize a color vector. So let's say this will be a vector of int, and let us also initialize the number of vertices in that particular graph. So in this case, it will be graph.size. And let us initialize it with -1. So this indicates that all of them are unvisited at the start. Unvisited or uncolored. Or we can also think of this as, let's say, white color. Okay. Now, our condition should be such that we have to iterate over all the vertices. Why we have to do this? Let me just put in this. So we have to iterate over all the vertices. The reason being that to ensure that disconnected, let's rather say disjoint forests, right? Disjoint forests are captured. So it can be such that, you know, we are taking some vertices from a particular subgraph and some other subgraph, and we want to see whether both of them are in the following the bipartite property or not. So we have to iterate over all the vertices. So we can do this by using auto I equal to 0, I less than n, I plus plus. Okay, and this will be our code logic. So our code logic is going to be checking if the node, right, if the node is unvisited or uncolored, or it is white, anyone. So if it is uncolored, that means it implies that it is -1 still, right? Then we will visit that node. Okay, and we're going to check that with that particular node, which is in question, particular node, checking whether our logic, that is graph coloring, which is the function that we'll be implementing, is returning true or not. Okay, if it is returning false, then it's false. So let us write this condition before moving on to the main part. So in this case, we are going to check if color of that particular node I is not equals to -1, and the second check we want to apply is, let's say this, we call this graph color function, and we're going to pass in certain attributes over here. So let's say graph, let's say the color vector and the node in question. So if this is true, and let's say if this is false, okay, let's write this as false, then in this case we are going to return a false, because in this case we have not found a suitable solution by using graph coloring. Else in all other cases we are going to return as true. Now with this driver function in place, let us try to write the BFS kind of graph color function. So it is going to be a Boolean function. So graph color, right? And we're going to take in the vector of the graph, and also we are going to take in the color. So vector int and color and the current index. So int. So we can also think of this as a vertex. Okay. Now first we have to make the color as, let us try to make this color, as 0. So making the color as let's say red in our case, that means visited. Okay. Now we have to initialize a queue. We are doing a BFS kind of a traversal. So we have to use a queue, right? And the queue should be containing an int. Okay. So this part is clear. Now the next part is applying a BFS traversal for each of the nodes in the queue, and just checking whether my adjacent edge or all the nodes which are there in my adjacency matrix, right, of that particular input node, which is IDX, we have to color it with a different color. So let's say if it is 0, then I have to color it with a different color, let's say 1, which stands for blue. And in the same way, If it is 1, that is already, it is blue color, then we can mark it with red. So this signifies red color. Okay. Q dot push. I'm going to insert this particular node. Now, while this is a standard BFS loop, okay, we have seen in the previous problems. Okay. So now we are going to extract the topmost element. So let's say the curve, let's say V. Okay, the vertex. Q dot front. Q dot pop. Okay. Now what we are going to do, we have to iterate over all the elements in the adjacency matrix representation of V. So let's say for auto J in let's say graph of V. Okay. So iterating over the adjacency matrix of an input node. So this is done. Now in this case, we have to check if the node is black or white. In our case, that means uncolored. Okay. So in this case, let me write it as if the color of J double equals to -1. So this indicates that it is still uncolored. That means we have taken the uncolored node as white. So it is still white. Now here two conditions arise. Two conditions. So what are the two conditions? So node can be red. Mark the J, that means the adjacent neighbor, okay, as blue. And the second condition can be node can be blue. Mark the J adjacent node as red, right? So there can be two conditions. So let us try to write these conditions. If let's say if the color of J, okay, if the color of J is 0, sorry, if the color of the V is 0, then I'm going to mark color of J as 1. Okay. And if color, let me write an else if condition here. If color of V equal to 1, then I'm going to mark it as 0. Now this will ensure that either or these conditions are satisfied. Okay. And if it is unvisited and if these conditions are met, we are going to push it back into the queue. So Q dot push. Okay. So we have to push back that particular node, which is this. Okay. Now there is another condition. So this condition is used to check if the node and its, let's say, adjacent node, adjacency J, is of same color. So that means that it is false. So else if the color of J double equals to the color of V. So this signifies that there is a conflict. That means same color in adjacent nodes. And we return it as false. Okay. So we return this particular part as false. I just shorten this. Okay. And if all other cases are running successfully, then we will be returning it as true. So this should be the core logic of what this entire algorithm is going to look like. So once we have written this, so if we were to summarize what we have gone through in this particular part. So we saw this problem as a graph coloring problem, and we have to iterate over all the edges, keeping a color vector in place. So color vector initializes each node with white color or -1, and we iterate through all the vertices or all the nodes in the graph just to make sure that it is a disjoint graph. Okay. And if the color of a particular node is 1, that is, it is unvisited or uncolored, or it is white in color. So, and the graph color for that particular node in question returns false, then it is a false answer. But And we use this graph color BFS algorithm where for an unvisited or an uncolored node, we first mark it as red. So from white, it becomes red. Now we push it into the queue, right? For each iteration of the queue, and for each, we pop that particular node, right? And we get the adjacency matrix representation or the neighbors of that particular node, right? And we check whether the color is -1 or not. So if the color is -1, that means that particular node is white in color. That means it has not been visited. So two conditions can arise in that case. If the color is white and if the parent color is red, then mark that color as blue. And if the parent color is blue in color, then we can mark the child color, let's say the adjacent node as red. So vice versa. And we push that particular node back into the queue. Now, a conflict may arise if the parent and the child or the adjacent nodes are of the same color, which is denoted by this particular logic here. So if color of J, which is there in the adjacency list representation of, or adjacency matrix representation of V, is of the same color as the parent node, which is V in this case, then we return it as false. And in all other cases, if all the queue runs to its final length, then we return it as true. So this should be the logic. And let us try to test the code on the sample input that we have here. So let me just minimize this. So for this particular example, 12302, and I think this is this particular example only. So it has returned a false, which appears correct. Let us try with a different particular input test case. It is very interesting to note that this graph coloring problem can be used along with BFS, can be used to solve quite a number of problems. So for bipartite checking, the algorithm should be that the graph coloring value should be restricted to 2. So here only 2 colors, that is we have taken red and blue. So we cannot take more than 2 colors, which is also bounded by the fact that we are doing this. If the graph is 0, then it will be marked as 1, and if it is 1, it is marked as 0. We can also think of it like color of J will be something like negatory of color of V, or this can also be written as 1 minus color of V, because this is also the same logic. If it is 1, then it should be 0, and if it is 0, it is 1. So this ensures that there are only 2 possible colors in the graph coloring algorithm for our use case. Okay, in all other cases, it will go to this particular else statement. That means, let's say we want to color 3. It will not color that to 3, but it will color to a repeated value of 0 or 1. In that case, it will go over here, else if condition, and it will return as false. So very important condition that only 2 colors are required for bipartite checking. So we see that this particular test case has returned as true, which is correct in our case. So let us try to submit this, and let's hope that this gives a correct answer. So we can see that this has given a correct answer. So it has run over all the test cases. So if we were to summarize, this is a very beautiful problem in the case of graph coloring. And always remember that graph coloring is used for checking bipartite, and this bipartite property can be used for solving many other such related problems. So there are problems in LeetCode which are related to bipartite matching, and this is one of the very tricky and very code conceptual problem which uses only 2 color way of graph coloring. So that's all for this video session, and I hope to see you guys in the next video tutorial on graphs.